Welcome to the thousands who are viewing here. I just wanted to spend a little bit of time talking about a few of the troublesome items on the test. I haven't finished grading the test yet. I'll probably won't have them done until the end of the week, but definitely before the beginning of the next week. Talk about a couple of those items and then just introduce forces. So I'm not going to be doing any numerical force problems today, but I'm going to be covering some issues that I think are really important for you to understand up front and to practice up front. And we'll also get to look at a couple old-timey pictures, and who doesn't like looking at old-timey pictures? So item number one on the test was this velocity versus time graph, and it shows the motion of an elevator. And a lot of times people think, well, in an elevator, does it just speed up the whole way? Well, it can't speed up the whole way because it has to stop at a certain floor. So they wonder, does it speed up to the middle and then does it slow down for halfway? So if you're going to the 10th floor, does it speed up to the 5th floor? Does it slow down then from 5th to 10th? This is a pretty good representation of an elevator. So it shows speeding up right there. It shows constant velocity right there, and it shows slowing down right there. And notice how most of the velocity here is constant. Most of the time it's at constant velocity. So it says here the motion changes at 3 seconds and at 18 seconds. Sketch the position versus time and acceleration versus time. So this here is showing, and let's just say that the dividing lines are here and here, and I'll use a different color. Let's use blue. In fact, I'll use 3 different colors. So for the blue section here, it starts off at a small velocity, goes to a medium velocity, goes to a large velocity. So that means, and remember that the slope of the position versus time graph is velocity. So that means that we've got a curve that starts off with a small slope, goes to a medium slope, goes to a big slope, like that. So here's the first section. The middle section is actually the easiest one to draw. But this graphing is difficult, so if you're saying to yourself, oh, he says it's easy, but it's really not that easy, that's right, it's not super easy. We're doing multiple representations. We're taking a verbal description here, so this is a verbal description. Translating it to a graph or graphs. And then down here, we're also going to relate it to numbers as well. And formulas. So the middle section has a constant velocity. Constant velocity means a constant slope upward like that. And then the last part, we'll pick a different color. Let's see here. Oh, I'll actually pick black for this one because my other 2 colors might be a little bit too light. This is a negative slope. So this starts off with a high velocity, goes to a medium velocity, ends up at 0 velocity. So that means we've got something like that. And this actually should be a little bit more continuous looking. Looks like I kind of shifted the slope here. But it's going to look like this. So at the top, that is a horizontal line. So 0 slope at the top. All right. So now it says determine the acceleration for each of the 3 portions of the motion. So if we call this section 3, we call the red one section 2, and if we call the blue one section 1, A1 is equal to delta V1 over delta T1. And it says here that its top speed is 7 meters per second. So it goes from 0 to 7 meters per second in 3 seconds because the motion changes at 3 seconds. So 7 minus 0 meters per second divided by 3 minus 0 seconds. That equals 2.3 meters per second, or meters per second squared. The next part is the red part, the lady in red. So here it starts at 7 meters per second, ends at 7 meters per second. So we've got 7 minus 7 meters per second divided by 18 minus 3 seconds, but of course that is 0. And then for the third part, delta V3 over delta T3. That starts at 7 and ends at 0. So remember, delta means final minus initial. So 0 minus 7 meters per second divided by T3. So the whole thing takes 23 seconds. 18 seconds is the where the motion started to go downward, or the velocity started to decrease, I'm sorry. So that's 23 minus 18 seconds, or negative 1.4 meters per second per second. So that's going to be down here, and we could label that how we want. The middle section is going to be 0. And the first section is going to be positive 2.3. Where most people had trouble on this one was the graph. A couple more items. One of the multiple choice items. Only 3 choices here. But this one is, I'm not going to say tricky, but once you get the answer, you're going to think that's kind of cool. So here is a building. Oh, let's do it right here. So one ball's thrown up, the other ball's thrown down. Both have the same initial speed. So here's a ball that's thrown up with this speed. It's going to do this sort of thing. And it goes straight up and straight down. I just made this curve here to separate more of the up and the down. And then another ball is thrown straight down at the same speed. So this is V0 blue. And this is V0 red. So V0 red, when it gets to the top of the motion, V top red is going to equal 0 for a ball that's thrown straight up. When it gets back down to this level here, so let's just use the green again. The velocity now is going to be downward, but V red here is actually going to equal the same magnitude, but just in the opposite direction of V0 red. So they're traveling at the same speed. And this would also work if it was off at an angle. The only thing is you'd then need to throw this ball down at the same angle below. So if you just throw this ball straight down and this ball out like that, those velocities are different. So in terms of when they hit the street. All right, so the last one, instructor goes to the roof. Roof or roof? Different parts of the country say it differently. Throws a golf ball straight down with a speed of 20 meters per second. So this one, I'm not going to do the whole thing, but I'm going to talk to you where there was a problem. So let's just kind of divide this up. Probably won't need this much space. Throws the ball straight down. At a certain V0. So what a lot of people did, I shouldn't say a lot, but this confused some people, I know, and I think they some of them started with this and then eventually went on to something else. But so people said, okay, we know V squared equals V initial squared plus 2AY delta Y. Well, AY equals negative G. So people said, V0 squared is 20 meters per second squared plus 2 times negative 10 meters per second. And it says that it's 20 meters tall. So times 20, that's going to be 400 minus 2 times 10 is 20, times 20 is 400. So V equals 0 at the bottom. But that is not right. And in fact, it's a little bit deceptive because this reinforces the notion. A lot of people say, oh, at the bottom it's 0 because it comes to rest. Hits the ground, it comes to rest. You made this mistake because you didn't carefully make note of your coordinate system. By saying that A is equal to negative G, we have set up your traditional XY axis like this. This tells us that up is positive. So if this is Y0 and we say, okay, that's 20 meters, and this is y, and this is 0 meters, yeah, we can still use v squared equals v initial squared plus 2ay delta y, but delta y, which is y final minus y initial, that's going to be 0 minus 20 meters, or negative 20 meters. So that means that v squared is going to equal 20 squared plus 2 times negative 10 meters per second times negative 20 meters. So we're going to be getting 20 squared plus 200. So that's not 0. So the lesson here, lesson to learn, carefully mark your coordinate system. All right, questions about that? Folks who are participating? You can verbalize them or you can put them in the chat window. All right, so we've got smart folks watching. They had no questions. Of course, that's misleading because that implies that smart folks don't have questions, but sometimes smart folks have the best questions, right? The dumb folks look at the world and say, oh, yeah, we're pretty happy with the world the way it is. One of my favorite quotes, and I'm going to be misquoting this a little bit, but I get the gist of it. Henry Ford, who, of course, was the one who, I don't know if he invented the assembly line, but certainly was the one who really made it popular and perfected it for his time. Someone asked him about market research and said, well, so you're making these cars. Have you asked the people what they want? And he said, no, I don't ask the people what they want, because if I asked them what they want, they'd say they want a faster horse. Everyone was riding on horses. They didn't understand this notion of a car that could be a lot better. So he, the smart person, said, I'm going to look beyond the horse. But the people who aren't certainly dumb but aren't thinking about things, oh, yeah, I'm fine with the horse, and sure, if I had a faster horse, that would be nice. All right, so we're now getting into the chapter on forces. So I want to go over just a few force concepts here. A lot of times words in physics have meanings that seem to be different from everyday life. So work and energy. Work actually is something that has a lot of different connotations, a lot of different ways that it's used in everyday life. Oh, this is so much work, or I have to go to work today. So it can be a place. It can be an emotion. Oh, I'm working so hard on this relationship. And really, you might just be thinking about it or worrying about it. Force is sort of one of those words, because we can talk about someone who's a force on the basketball court. Maya Rudolph may be a force on the basketball court, or we can talk about someone who's a force in the world of science. Isaac Newton was a force in the world of science. Interestingly enough, he was one of the people that really formulated our views of what forces are and how they interact with each other. But really, a force is just a push or a pull that's exerted on an object, so that affects the motion of an object. So affects the motion doesn't necessarily mean that it makes it move, but if that force wasn't there, it would be moving differently. So here's an example of a physics book. on a table, two forces acting on it. The Earth is pulling it down, the table's pushing it up. So neither one of these forces, you'd think, are making it move because it's not moving. But if we took one of those forces away, if we took away the table, let's take away the table. I should have done a little bit of magic here so I could take away the table, but if we took away the table so that that force disappeared, then this book would accelerate downward. So having the table there affects the motion of the object, because without the table it would have a different motion. But we want the table back. All right, so we've got the table back girl. I've got a rule for naming forces, because a lot of times we'll just give a force a one-word name, like the weight, or the normal force, or friction. But it's important to recognize that forces, there are different types of forces. So that's what this first blank indicates. And there are different things that exert those forces. Some common one-name forces that we'll have in our class, gravitational force, contact force are probably the two most common. Elastic force, friction is pretty common. Tension, which you could argue is a contact force, is pretty common as well. Remember that force is a vector, meaning it has a magnitude and a direction. So this force and this force are different from each other, even though they're the same strength. One's pointing up, sort of, one's pointing down. So if we look at the forces right here that my thick blue arrow is pointing to, let's use our naming rule for those. So this one is pointing downward, and its gravity here is somehow influencing it. So if I were to name this force here, I would say this force, using my rule, is the gravitational pull of the Earth on the book. So notice I've mentioned what is doing the pulling or pushing, in this case pulling, and what is being pushed or pulled. So this one, the table is pushing upwards. This actually is a contact push. So this would be the contact push. Oops, that didn't turn out very well. I'm going to delete it. I was trying to use the little fancy thing on the side of my pen here, and that didn't work. Of the table on the book. So notice once again, we've got what's doing the pulling or pushing. And what is being pushed or pulled. So I should have been more strategic with my circling here. So the object that the force is being exerted on and the object that's doing the pushing or pulling. And then you could also say, well, what about the name of the force? So contact push, gravitational pull, the blank push or pull. So it's really good to practice using these names because that helps you go over what forces must be on your free body diagram, which we're going to talk about next. Because you could look at this situation and say, well, what about the floor? This table, well, let's use a different color. So this table is on a floor. Are we going to worry about the floor's influence on the table? We're not, because if we were to fill this out, we would say the contact push of the floor, but the floor is not touching the book. The floor is touching the table. So that doesn't end with on the book. When you're doing this, you know you've got a properly labeled and a properly utilized force when the last phrase is the object in question, so the book in this case. So let's do the free body diagram on the person here, or on this person and sled. Let's use red here. So here's the first of our old-timey photos. We're going to draw the free body diagram of the people. So our system then is people and sled. And it looks like this might be an animal. It almost looks like a big cat here, at least in my resolution of the picture. It sort of looks like maybe that's sitting in front or on our side of the sled, so to the side of the sled from these people's point of view. So let's just ignore this. It's the people and the sled. So what are the forces acting on this? Well, there's this one. That's the Earth pulling down. There's this one. That's the ground pushing up. And actually, I'm going to shift these. And just so it doesn't look so much like the other, I'm just going to make it a different color. Sorry about that. I should have planned a little bit better. And then there's also, I'll go back to red because red I think shows up best on the picture. There's this pull right here. We'll call that 3. And there's probably a little bit of friction. We'll call that 4. So these are all external forces acting on the sled. So force 1 is Earth on the system. Force 2 is the contact push of the ground. On the system. Force 3, you could call that a number of things. Let's see, the book uses some different nomenclature. The force, yeah, we could say that's the contact pull of the handle, maybe. On the system. And then number 4 is the frictional pull of the snow on the system. So notice all of these end with on the system. And all of these others here, earth, ground, handle, snow, these are the things that are creating the force. So drawing them like this, just sort of disjointed out from the system here, isn't the best way to do the algebra. So oftentimes they will be sketched on an XY axis. So this one, I'll try to make it relatively close. I'm just using a ruler here on the screen. Looks like it goes down to about there. Oops, sorry. Still haven't mastered this. Oh, and the book likes to use the lowercase f for this. This could be force of the handle. So any sort of weird applied force, the book likes to use that. Contact push of the ground on the system, the book likes to use that, which stands for normal. And normal doesn't mean sane, normal means perpendicular. And the gravitational pull of the Earth on the system, that is the nickname for weight. All right, one of the best songs by White Lion. Maybe their only song. So this is W. This is N. This is F handle, and this is the friction, and this is at whatever angle that is right there. I went through this thought process fairly long and detailed. You certainly don't have to do that every time you make one of these sketches, but you really should focus on making a careful free body diagram. So a carefully drawn free body diagram really helps you solve the problem. And in fact, this is more physics here, drawing this diagram, than actually doing the algebra. All right, this is a picture that I got from the internet. Oh, and by the way, all the pictures that I'm using, the sled, this one, and then one that I'm going to use later, they're all public domain pictures. So you can just search online public domain images. And Wikipedia, for the most part, is all public domain images. I want to say that it's all public domain, but they may have some that are proprietary, and of course they may have some that someone just snuck up there before the Wikipedia gurus have taken it down. But anyway, this is the a shuttle fuel container, and this is a view from up above. The blue that you're seeing here is actually ocean water, and these are clouds looked at from above. So it kind of looks like you're on the ground looking up at the sky and this thing's coming at you, but it's really the opposite. So let's say that this one is empty. And that this one is full. So if we're to draw a free body diagram, so free body diagram, another thing, I didn't mention this before, but notice how I made the arrows different lengths. I tried to make the arrows roughly proportional to the force that they exert. And we'll talk more about that later. I probably made the handle force too long compared to the weight, because these two people in their sled, well, let's see, these are, if they're normal adult, and this was from the early 1800s, so people weren't as overweight like a lot of folks seem to be today. So let's just say they average 150, so 300 pounds. Wooden sleds, maybe an additional 50 pounds, so 350 pounds. So this arrow is 350 pounds long. This arrow is about 2/3 of it, so this is showing something that's maybe 225. That's a pretty big force for a horse to exert on the handle like that. But I definitely showed the friction shorter. I showed the normal force shorter, and you might ask now, why is that? We'll talk about that later, or you'll read about that in the book later if I don't talk about it. So for this one, make the arrow length roughly proportional to the strength of the force. So obviously a full fuel container is going to be a lot heavier than an empty one. And there might be a tiny frictional force for each of them, and that would be related to their cross-sectional area. So this is the weight of the empty one. There's the friction on the empty one. There's the weight of the full one. There's the friction of the full one. So the frictional force of the empty one is going to equal the frictional force on the full one. So frictional push of the air on the tank or the container is the same on each. So I drew one of these arrows about 8.5 centimeters long and the other one about 3. So let's analyze this a little bit. So one of them, like I said, was about 3, and the other one was about 8.5. So according to Newton's second law, and let's say for this one, let's just assume here that the frictional force is much less than the weight. So if you've never seen that terminology before, that symbolism before, this means much less than. All right, so Newton's second law says the net force, and so it uses that. I was just taking a quick look in the book. Sometimes they use this Greek summation sign. So this also means the sum of. So the net force equals ma, and here the net force equals W sub E. Here the net force equals W sub F. So let's look at the acceleration. So if we solve for acceleration, so acceleration equals net force over m. So here we've got a certain acceleration that equals the net force, which was W sub E divided by the mass of E. Over here, so that's the acceleration of the empty tank. Acceleration of the full tank, that's equal to, again, net force over m. But here the net force is a lot bigger. Divided by m, which is also a lot bigger. So here we've got a big force divided by a big mass. My divided by line kind of bent over there. Here we've got a small net force divided by a small mass. So the acceleration is the same in each case. Which is a pretty surprising result, because you could say, well, the Earth pulls on the more massive one with a greater force, and that's true, but it also has a larger mass. So larger pull, larger mass, and those two terms cancel each other out. Here we've got smaller pull, smaller mass, same value, same quotient. One more, let's just practice drawing the forces on this one here, this cable car. Let's go with the red, the cable car in red. So our system is the cable car. So in this case, there's going to be the gravitational pull of the Earth on the car. There's going to be the contact push of the ground on the car. There's going to be the force of the cable on the car, and then a little bit of friction. So let's sketch this now. Notice that we've got two of these forces on a hill. So and one is perpendicular to the hill. So if we just quickly redraw it here, so we're going to have a force that's downward, one that's upward that way, so up from the road, one that's this way, and one that's that way. So if we're going to analyze this, we have a choice to make. And when we make our coordinate system, typically I draw the traditional coordinate system like that. But that's not always the best one to use. And in fact, this time, we're not going to use the traditional coordinate system. We're going to use a coordinate system that is tilted at the same angle that the road is tilted. Oh, I don't need to write that. That's just going to be the same. So if we do our forces, let's actually make this a different color. Now, we're going to make the x-axis is going to be parallel to the road. And the y-axis is going to be perpendicular to the road. So N is perpendicular to the road. The force of the cable is parallel to the road. Frictional force is that way. And I didn't say this before, but we're assuming that cable car and it's getting pulled up the hill. The weight was actually the only force that's not on one of our tilted axes. So the weight is going to be down like that. And that's going to be off at an angle theta. It turns out that the value of that angle theta so if this is how much the road is tilted, so this is that means that this is going to be theta right here. So we've got forces then at different angles. So notice in this case, the contact force and the weight are not opposite each other. And also notice the force of the cable and the frictional force are not the same as each other as well. And then theta is a little bit tricky. The way that I remember that is if I were to flatten this hill, if this hill here were to flatten, theta would of course go to 0. And flattening this means having this axis rotate downward, which means that this axis would rotate towards the weight vector. All right, so a lot of conceptual stuff, but understanding this is important. So this, you'll be using this tilted coordinate system in some of your homework problems. And actually, while I'm writing, I'm just about to end here. If folks have any questions, you can put them into the chat box. And notice that one benefit of this is that the acceleration is only in the x direction, which is along the hill. In a traditional coordinate system, there would be acceleration in both directions, x and y, because it would be going sort of up and to the left like that. Alrighty, well thank you. Hopefully that helped things out in terms of sketching forces. Next time we're together, I'll do some numerical problems. But really, making a careful diagram and picking up an appropriate coordinate system gets you a great start on the problem. Thank you.